So what we're leading into now is a larger discussion where we combine all these reactions together. So we have four reactions that we're talking about: E1, E2, SN1, and SN2. And we are going to find out that they're all linked because they all use halogens. So what we're going to do now is just summarize what did we just learn about E2 and E1, and then we're going to start saying how are these reactions connected. So the elimination and the substitution reactions, how are they connected together? And then we're going to come through and do a summary where we talk about what reaction is occurring. So we just got done talking about the elimination reactions. During an E2 reaction, the one thing you needed to remember is that it uses a strong base. And when I say a strong base, we're going to find out, yeah, there's a lot of strong bases in organic chemistry. For this class right now, when I say a strong base, I mean hydroxide or an alkoxide. So with alkoxides, they can be things like methoxide or ethoxide. And the reason why we want this strong base, remember in an E2 reaction, the base comes in and removes a hydrogen. So it needs to actively act as a base, go in and remove a hydrogen. So the idea here, and this is where it gets a little tricky, some good nucleophiles, so lone pair electron and a negative charge, are actually also a strong base. And so there's a little bit of confusion. Does it want to act as a base or does it want to act as a nucleophile? So in some cases, hydroxides and alkoxides act as bases. Sometimes they act as nucleophiles. And we'll talk about, okay, which one's which. But this is the idea. In order for an E2 reaction to occur, I need a strong base, like a hydroxide or an alkoxide. E1 does not need a strong base. It can have a weak one. And just like with SN1 reactions, in an E1 reaction, the base kind of sits around and waits for the halogen to pop off and for a carbocation to form. And when this happens, the weaker base can come in and remove a hydrogen and form the double bond. One of the things you want to remember, so remember there's idiosyncrasies with these reactions. So with both elimination reactions, we need to remove a hydrogen from the adjacent, from a carbon adjacent to the halogen leaving group. And that's true for both of them. So let's go back through and say, well, what happens when we have something like a nucleophile that's also a strong base? So remember, hydroxides and alkoxides can either act as a base or it can act as a nucleophile. And what's some of the things that can separate those two out? What's left over? What tells the species to act as a base or act as a nucleophile? So there's actually a competition between elimination and substitution reactions. So remember, a good nucleophile is involved in an SN2 reaction, a strong base is involved in an E2 reaction. Well, my good nucleophile and my strong base are actually the same thing. And so we need to decide what causes a species to act as a good nucleophile, what causes a species to act as a strong base. So part of the reason why this is true is in the SN2 reaction and the E2 reaction, my nucleophile slash strong base is involved in the rate determining step. That's because both of these reactions only have one step. So my nucleophile slash base are involved in the rate determining step of SN2 and E2. So that's the idea, is species like my hydroxide and alkoxide can act as a nucleophile in some cases and can act as a base in some cases. And what's going to be the difference now is that SN2 reactions are slowed by sterics. E2 reactions are not slowed by sterics. So the answer to the question of will my hydroxide and alkoxide act as a nucleophile or will it act as a base, the answer depends on what kind of halogen do I have. So we go back through, remember we use the designation primary, secondary, and tertiary for our halogens. We need to remember that SN2 reactions don't like sterics, that it's hard for us to get an SN2 reaction with a tertiary halogen. But E2 reactions are not affected by sterics. So what do I mean by that? So remember the mechanisms of SN2 and E2 are kind of distinctly different. They're both bimolecular, yeah, they're both one step, they're both concerted, they both involve the nucleophile slash base. But one big difference is what are they actually attacking? My hydroxide and alkoxide, what are they actually attacking in an SN2 reaction and what are they actually attacking in an E2 reaction? And so we're going to see the big difference is SN2s what's the big difference between an SN2 and an E2 reaction? SN2 reactions are affected by sterics. E2 is not. So let's take a look at this, and this kind of puts it straight out. I have my good nucleophile slash strong base, and I have a decision to make. Does it want to act as a nucleophile? Does it want to act as a base? And the idea is my alkoxide, my ethoxide, is going to attack two different atoms, depending on whether I'm talking about SN2 or E2. So during my substitution reaction, my SN2 reaction, the alkoxide, if I want to try to make it act as a nucleophile, actually attacks this electrophilic carbon. So if I was to draw out the mechanism, there'd be an arrow coming from this lone pair electron attacking the electrophilic carbon. The problem is my electrophilic carbon is very crowded. It's surrounded by 3 methyl groups, and it comes down to literally size. It's going to be hard for this group to come in and attack this carbon to kick out my leaving group. So remember, SN2 reactions have backside attack. It's going to be very hard for my ethoxide to act as a nucleophile and come in here and attack this carbon. And I guess one thing I should point out, this halogen is a tertiary halogen. So remember, the carbon that's attached to my leaving group is attached to 1, 2, 3 different carbons. And we already discussed the fact that you can't really get an SN2 reaction with a tertiary carbon. And that's why, because of the sterics. It's really hard for my nucleophile to get in to attack this carbon because there's all these other carbons around it blocking. So here, this SN2 product, so this would be the product if I did an SN2 reaction, this is not going to form. But the idea here is when I do an E2 reaction, I'm not attacking the electrophilic carbon, I'm attacking an adjacent hydrogen. It's completely different. So if my ethoxide wants to do an E2 reaction, it acts as a strong base, it attacks the hydrogen. The hydrogen is not in the center of all these groups. These hydrogens are kind of on the periphery. That's why E2 reactions are not affected by sterics, because they're not going for the electrophilic carbon. They're going for the adjacent hydrogen, and the adjacent hydrogens are kind of on the outside. We don't need to get all the way into the electrophilic carbon. In order for my ethoxide to act as a base, it attacks one of these hydrogens. The hydrogens are on the outside. So during an E2 reaction, remember, I remove an adjacent hydrogen, I remove my leaving group and draw a double bond across here, so I get an E2 reaction. So this is the big difference. And we're going to see this. A lot of what chooses our reaction is what type of halogen do I have. But the idea here is if I have my good nucleophile strong base, and it could go either way. So my alkoxide could act as a nucleophile or it can act as a base. It's going to act as a strong base when I have a secondary or tertiary halogen because of the sterics. So in this case, it was a tertiary halogen. I'm not going to get a substitution reaction. I'm going to get an elimination reaction. That's because my electrophilic carbon is too sterically hindered. So the opposite is true, though. If I have a primary halogen, there's not a lot of sterics around that halogen. There's mainly hydrogens. In this case, my good nucleophile slash strong base is actually going to undergo an SN2 reaction. So we'll look at that in just a second. That's the big difference between E2 and SN2 reactions is sterics. Low sterics, by that I mean a primary halogen or primary leaving group. Low sterics, SN2 reaction. High sterics, secondary and tertiary halogens, E2 reactions. So that's how we tell the difference. Of the other two reactions, SN1 and E1, remember they are linked together. If I get one, I get the other one. So in reality, there's only kind of 4 reactions that we have. We only have 3 reactions. I can either get SN2, E2, or the SN1, E1 combination. So now what we're going to do is come through and look at a flow chart, and the real question is, given an example, what reaction's occurring? And that's what we're going to look at right now.